Okay, from now on and in the next a number of lectures, we are going to discuss oxygen transport in biological systems. And this lecture is an introduction on the basic terminology and the relationships we are going to discuss, which is partial pressure of oxygen and Henry's constant. So first, let's just go through what is partial pressure. So partial pressure of oxygen is written as P, O2. This P means partial, O2 means oxygen. So this is the symbol for partial pressure of oxygen. So you can define partial pressure of any gas. You can define PCO2, that is partial pressure of carbon dioxide. So the definition of any species of gas, like the partial pressure of it is the pressure, which is the percentage of the one atmosphere. So we have one atmosphere that has certain pressure. And if you have a gas which is 20% of the atmosphere, then the partial pressure of that species of gas would be 20% of the pressure of the atmosphere. So this is the pressure that contributed by that type of gas within the air environment. So partial pressure are usually given in like expressed in units. Expressed in millimeter mercury. So we have seen these units when we talked about like osmotic and hydrostatic pressure when we discuss solute and the pressure in within and outside of blood vessel and when we discuss capillary filtration. So we will still use millimeter mercury. The discussion of partial pressure is originated or in the context of oxygen is we want to know the oxygen concentration in the body. But in many experimental and clinical contexts, the concentration of oxygen is not expressed directly in molar units. So we have been dealing with molar units in this class a lot. And we call it C, like it's mole per unit volume. However, in clinical context, people usually use partial pressure to refer to the oxygen level in the body. So this convention stems from the behavior of gases and the practical ease of like measuring gas phase pressure relative to directly measuring concentration. So we would like to know, for example, in the body, what's the concentration of oxygen in the blood or in general. In order to know the concentration in the liquid we are interested in, and what's its relation to the partial pressure in the air, that's what Henry's constant is doing. So think about it, you have a tank. So you have liquid. Here you have air. Oh, like a gas phase. Let's just say gas phase. And then within the gas phase, you have partial pressure of oxygen at a given temperature. So at a given temperature, the temperature matters. We will discuss soon that this process depends on temperature at a given temperature. So in the liquid, we would have the concentration of oxygen in the liquid. So we have C, oxygen. And you want to know how's the relation between these? Of course, intuitively, you know that the higher concentration the higher partial pressure of the gas in the gas phase in the air would lead to a higher dissolved concentration of that molecule in the liquid. That's exactly the case. So this relation is given by we call the Henry's constant. So CO2, the partial pressure of O2 in the gas phase, it's equals to the Henry's constant for oxygen multiplied by the concentration of oxygen. So this PO2 is partial pressure in the gas phase. This is Henry's constant. And this C oxygen this is the oxygen concentration in liquid. It is usually expressed in micromolar. So that you know that the units of a typical unit Henry's constant would be millimeter mercury per micromolar. And we have been saying that this is temperature dependent. So usually at a higher temperature, the dissolvability of gases in the liquid reduces. This is because as temperature increases, it has a large impact on the kinetic energy to gas molecules. So this reduces their tendency to remain dissolved. And for oxygen in water, let's say, just give you some like intuition of like what Henry's constant look like and how they differ by temperature. So for oxygen in water, for oxygen in water. At 0 degrees C, Henry's constant equals to 0.349 millimeter mercury per micromolar. And at the 40 degrees C, 0.738 millimeter mercury per micromolar. So it almost doubles. And you can see the significance of the impact of temperature. So this is an introduction of Henry's constant and how to use Henry's equation to relate the concentration in the gas phase versus the concentration dissolved in the liquid phase, which is in equilibrium with the gas. So we consider the liquid and the gas phase, the two phases are in equilibrium. This is how they related. Now let's talk about the Henry's constant for oxygen in blood. Oxygen in blood. It also varies at in temperature. So we are interested in at a body temperature or at a physiologically relevant temperature. So at 37 degrees C, it is approximately approximately 0.74 millimeter mercury per micromolar. So this will be the value we will use a lot for the at least for this group of topics on the oxygen, like distribution in the body or oxygen transfer in body tissues. So let's look at an example. Consider an aqueous solution. Or consider a liquid solution. At 25 degrees C. At this temperature, Henry's constant for oxygen in water. So at this temperature. And 603 millimeter micromolar. And if the partial pressure in the gas phase above the solution is 100 millimeter mercury, so if the partial pressure of the oxygen in the gas phase above the solution 100 millimolar mercury, find the concentration of dissolved oxygen in the solution. Find the concentration of the dissolved oxygen. So to solve this problem, we will directly use the Henry's equation. So now we are going to find oxygen, the concentration of oxygen. So we rearrange this equation. So to solve for this, it equals to partial pressure divided by the Henry's constant. So it is 100 milliliter mercury divided by the Henry's constant, which is 0.603 molar. Just putting the number, you can see the pressure cancels, so you get the concentration 165 or 1.84 picomolar. So this is how we use it. Okay, let me leave an exercise or a homework for you. So here is the homework problem. An experimenter measures the partial pressure of oxygen above two separate water samples. So one is at 10 degrees C and another is at 35 degrees C. So the Henry's constant for oxygen at these two temperatures are given. The partial pressure of oxygen above each sample is the same. So you ask you to calculate the ratio of dissolved oxygen concentrations in solution under these two temperatures and comment on the physical significance of your result.